Hello everybody, this is Dr. Christopher White, and in this presentation we're going to start thinking about the process of plate tectonics. So this presentation is going to correspond to section 3.1 of your textbook. So before we get going on the theory of plate tectonics, we need to start by thinking about some of the observations that early geologists started making and how these early observations made these geologists begin to think maybe there's some kind of large-scale process taking place. So if we look at our globe here, we can see that it is not a uniform surface. We can see there's lots of variation. Now the major type of variation, and one we're already familiar with hopefully, is the fact that we have the continents and the ocean basins. And we know that the continents are dominantly made up of continental crust, which is thicker and lighter. And we know the seafloor is made up of oceanic crust, which is typically thinner and denser. And we've already discussed how the difference in thickness means there's a difference in the relative height of these two different types of crust. So the oceanic crust being thinner forms topographic lows, and the continental crust being higher forms topographic highs. So we've already covered that in the past, but now we need to start thinking to ourselves, well, why is there all this variation that we see in the ocean basins and on the continents? There's lots of stuff going on. So if we look at our globe here, what we've got is we've got several different areas highlighted around the margin. So for instance, we need to explain features like the Pacific Northwest. So you're thinking to yourself, okay, there's a mountain range there, but why? And why does that mountain range have earthquakes? Why does that mountain range have volcanoes? We need to be able to explain these observations. We can also begin to see some stuff going on the seafloor off the western coast of the Pacific Northwest, which we will also look at in greater detail. So we need to explain what we're seeing on the seafloor as well. So, for instance, we also need to explain South America. So when we look at South America, what can we see? Well, we can see over here on the eastern margin that the terrain is relatively flat. We can also see that some of the continental crust is actually covered by seawater. We can see it here as these lighter blue areas where the water is pretty shallow. But one thing we can't see is we can't see any kind of activity going on. In contrast, on the western coast of South America, we can see that there's lots of stuff happening. We can see straight away we have this long linear feature on the seafloor right there, marked out as this dark blue line, but we can also see, of course, we have the Andes, so we have another mountain range, and this mountain range is very active. There's lots of volcanoes and there's lots of earthquakes going on. So why do we have these two differences? Why is one side of South America relatively flat and relatively boring, whereas the other side of South America is a very active geologic environment? We also have to look at the seafloor, and a very nice example of the seafloor would be the South Atlantic. So when we look at the South Atlantic, we can see we've got Africa over here, South America over here, and we can see we have this raised ridge which is running down the center of the South Atlantic Ocean basin. We can also see that this raised ridge is not one continuous straight line. It's actually a zigzag. It's stepped, and so we'll see this in greater detail in a couple of slides time. But when we look at this, you'll notice that the ridge comes down, across, down, across, down, across. So it's like a set of steps. It's not one continuous line. So obviously geologists have to think to themselves, right, why is this ridge running down the middle of the ocean? Why is it higher than the surrounding seafloor? And why does it have this stepped pattern to it? So this is something else that geologists have to try and explain. Now, we see the same kind of things happening over in the Arabian Peninsula. So obviously over here in the southeast of the image, we have the Indian Ocean basin. But once again, if we look here, we can see a stepped pattern right there, just like we can see in the South Atlantic. We can also see, once again, we have a set of mountains up here. And here, which is the Red Sea, appears to almost have a giant crack running straight up the middle of it. And then, of course, we have this region here, which is the Afar region, which you can see is a very tectonically complex region. So you can see that because it's an area of elevated terrain in an area which is otherwise really, really flat. So what's going on there? So we can see, once again, there's all these little things going on which we can see which have to be explained by geologists. So over here we obviously have Japan. So what do we see? Well, we can see we have a couple of areas of seafloor. We have one area of seafloor over here on which Japan is sitting. And we have another area of seafloor down here which represents the Pacific Ocean basin. And once again we can see another one of these long, thin, essentially gorges, trenches running along the seafloor here. So this is an area where the water gets very, very deep, so the seafloor has dropped down quite a lot. Now, one of the things we'll notice is that these lines of islands which form here, they're very volcanically active, and they have a curved shape to them. In fact, you can see this curved shape very nicely right there, and you can also see the same curved shape actually for Japan as well. So the question then becomes, once again, why do we have this trench running along the seafloor here? Why do we have these curved chains of islands, and why are these islands volcanically active? And then finally up here we have Tibet. Of course, we know Tibet formed as part of the process that gave us the Himalayan mountains. So we can see the Himalayan mountains running along the southern edge here. And behind it we have the Tibetan Plateau, which is essentially an area of raised crust which is on the whole relatively flat. And so we have to ask ourselves, well, why do we have all of this topography up here, yet India to the south is, comparatively speaking, relatively flat? So we need to explain what we're looking at, and geology is the only mechanism that really allows us to try and explain what's happening. And obviously whatever processes are causing these events or causing these variations that we can see, they obviously have to be pretty big, pretty powerful processes. Okay, so here's our picture of the Pacific Northwest. So to begin with, straight away we can see we have two distinctly different domains. On the eastern side of the image, we clearly have an area of continental crust, and on the western side of the image, we have an area of oceanic crust. So what can we see? Well, with respect to the oceanic crust, we can see a couple of interesting features. Number one, we can see here, there is a very distinct feature running approximately east-west, and it's actually creating a step on the seafloor. So there's what we refer to in geology as a scarp. So there's a scarp that's running along the seafloor right here. We can also see that there's differences between this piece of oceanic crust here and this piece of oceanic crust here. You'll notice that this piece of oceanic crust is, on the whole, relatively flat. It gets a little bit more complex over here, but this area here is, on the whole, relatively uniform. In contrast, when we look at this area here, we can see one of these zigzag patterns that we were speaking about earlier. So we can see so it's starting just here, and it's coming up, across, up, across, up. So we have this zigzag pattern. We can also see that the ridge that's forming along this zigzag pattern is standing higher than the surrounding seafloor. So this area over here has a greater elevation than this area of flat seafloor over here. In terms of the continental crust, we can see over here we have an area of Canada and some of the northern states of the US, which is on the whole pretty flat. We can see it's also pretty poorly drained because we have the build-up of these bodies of water in the form of lakes. Now, as we move westwards, what do we see? Well, we can quite clearly see we have this increase in elevation in the form of a very large, very broad mountain range. And this mountain range is starting up here all the way in Alaska, and it's coming all the way down the west coast, and it's continuing down into Mexico. So we need to explain what we're looking at. So let's highlight some of the features. So straight away, this is this step in the seafloor, which is running approximately east-west there. In geology, as I said, that step is typically referred to as a scarp. Now, if we go to the north of it, we can see we have this ridge feature. So this is this area of raised seafloor that forms this very, very distinctive zigzag pattern. Over here in our mountainous terrain, we have an area which is volcanically active. Now, the interesting thing is that this entire mountain range isn't all volcanically active. So we know that some parts of it are and some parts of it aren't. So for instance, we know the area down here, which is California, although we have the elevated terrain, we do not have volcanoes. Now, this area here, which is referred to as the Cascade Volcanoes, essentially extends from northern California through Oregon, Washington State, and then up into southern British Columbia. So we have a region that starts approximately here and continues up to approximately here, which is volcanically active. And then we return to a situation where the terrain becomes elevated, but it is volcanically inactive. And so we need to be able to explain this. Why do we have this elevated terrain, and why are some parts of it volcanically active and other parts of it not? So you can see there's lots of stuff that as a geologist we have to try and answer. Okay, so now let's move on to South America. Now, as mentioned, South America is a continent that shows two completely different environments. Over here, on the eastern side, we can see the terrain is relatively flat, and we can see that some parts of the continental crust are actually covered in seawater, and it's marked out by these lighter blue areas that we can see here. So this is an environment which is referred to as the continental shelf. And the continental shelf is an area of continental crust that is covered by seawater, and the water is typically quite shallow. It's anywhere between about 0 and 200 meters deep. So, you know, might sound a lot, but in the grand scale of things, 200 meters isn't a huge amount. Now, you'll notice there's no mountains. You will notice there's no obvious volcanoes. And on the whole, this area seems, geologically speaking, relatively quiet. We can see there's obviously some rivers. We can see the estuaries for the rivers here. But apart from that, not too much going on. In contrast, over here on the western side, we can quite clearly see there is a lot happening. So we can straight away see this area of elevated terrain, which of course we know are the Andes Mountains. Now, we also know the Andes Mountains are very tectonically active, so there's lots of earthquakes, and we also know they're very volcanically active, so we know there's lots of volcanoes and volcanic eruptions. We also can see just off the coast that there is this long linear feature running down the western side of South America. Notice there is not a corresponding feature on the eastern side. So this is what we refer to as a trench, and it's a linear depression on the seafloor, and these trenches can get extremely deep. So if you think of the deepest point on the seafloor, which is the Marianas Trench, that is one of these trench systems, but that one's over by the Philippines. So these trenches are areas where the seafloor drops down very, very quickly, but it does so in a very narrow area. So as a geologist, we want to explain, why do we have this trench here, but we don't obviously have a trench over here? What's going on? There's something clearly happening. So if we just highlight some of the stuff we're talking about, here's this trench running along the seafloor. We need to explain why that's there. Obviously, we have the Andes Mountains, which I should have highlighted in white, but clearly I wasn't concentrating when I did that. So you just have to take my word that it's there. And then in contrast, we have this low relief interior. So you can see the terrain is relatively flat. There aren't really any mountains. There's not much indication of, geologically speaking, too much going on. And then over here we have the continental shelf, which is this area of continental crust which is covered by seawater to depths of 0 to 200 meters. Now, South America allows us to bring in two terms that geologists will regularly use, and these terms are active margin and passive margin. So in geology, an active margin is essentially defined as the coast of a continent which is geologically active. So it means there's going to be a mountain range, there could be earthquakes, there could be volcanoes. There is some kind of major geologic process going on that is disrupting the crust. Okay, so the western side of South America would be classified as an active margin because we can see the terrain is mountainous, we know there are volcanoes, and we know there are earthquakes. In contrast, the eastern side of South America would be classified as a passive margin. Geologically speaking, it is quite a quiet environment. So we don't have mountain ranges being built, we don't have volcanic activity, we don't have earthquakes happening. The major process that's occurring along this passive margin is one of erosion and sediment deposition, and that's pretty much it. So you can see we have these two contrasting environments in South America, the active western margin and the passive eastern margin. Okay, so here we are in the middle of the South Atlantic. Obviously we have South America down here and Africa over here. And here is this ridge that's running down the center of the South Atlantic. You can see it quite clearly. So straight away we can see that this ridge is topographically higher than the surrounding seafloor, and this is a very important point. This ridge and the land and the seafloor either side of it is higher up than the seafloor over here, so we have to explain that as geologists. We also have to explain why we appear to have this giant crack running down the middle of the South Atlantic Ocean. But also we have to explain why it has this stepped pattern. So notice we have what looks like a giant crack here in the form of the trench. But we know this trench is of course an area where the seafloor drops down very, very quickly. In this case, we have a raised area of seafloor that has a crack running down or looks like a trench-like feature running down the middle of it. So we have to explain, why there are these two differences. We also have to explain why we have these steps, and you can see it quite nicely right here. So here's our ridge coming down. It steps, comes down, steps quite a lot, drops down, steps a really big amount there, drops down, steps again, and then so on down here. So we have to explain why this particular area of raised crust has this very, very distinctive zigzag pattern to it. What's going on there? So obviously we have our ridge, which is our raised area of seafloor, and it's this linear feature running down the middle of, in this case, the South Atlantic, but there are lots of ridges all over the world, so don't think this is the only example. We also have this smooth seafloor over here, which is topographically lower. So the ridge is an area of raised seafloor. The seafloor either side of it is, topographically speaking, lower down. We obviously have passive continental shelves on both sides of our margin. So notice here, here's our eastern coastline of South America, which we were discussing, is a passive continental margin. And over here we have the northwestern and eastern coastline of Africa. And you can see once again, no volcanoes, no mountain building, no earthquakes. So once again, we would classify this as a geologically passive margin. And of course, when we're thinking about our ridge, we need to explain this giant crack that we can see running down the middle of it. And we need to explain this stepped pattern, this zigzag pattern that we can see quite clearly. So there's lots of things that geologists have to answer. Oh, and of course, then we have these what appear to be linear features running approximately east-west, cutting directly across our ridge. And so we need to explain what these fracture zones are as well. So what about Tibet? So as we discussed, the formation of the Tibetan Plateau is part of the process that gave us the Himalayan mountains. And we can see the Himalayan mountains quite clearly right there. And so the Tibetan Plateau is this area to the rear, so to the north of the Himalayan mountains. And you can see it's an area of elevated, so it's high terrain, but on the whole, it's relatively flat. So why has this area been lifted up, giving it mountainous terrain, versus India down here, which is, as you can see, on the whole, pretty flat? So the other thing we have to explain though is, okay, the mountains we've seen so far have been along coastlines, haven't they? So we saw the mountains of the Cascades, and we also saw the mountains along the west coast of South America, the Andes, but that's where we have continental crust meeting oceanic crust. In this case, we have a situation where we clearly have a piece of continental crust here and more continental crust down here. So why do we have the mountain range? So clearly we are forming a mountain range, but this mountain range is forming under a different set of conditions, and we have to explain what's going on. The other thing about the Himalayas and the surrounding Tibetan Plateau is that, yes, they are tectonically active areas, so we know there's lots of earthquakes. But unlike areas like the Andes and the Cascades, the Himalayas and the Tibetan Plateau to the north of it are very volcanically inactive. There aren't many volcanoes. So we also have to explain why we have this mountainous terrain here, which does have earthquakes, but is relatively volcano-free. Compare that to the Cascades or the Andes Mountains, which are absolutely stuffed with volcanoes. So why is there this difference? So if we look at some of the features, we obviously have the Tibetan Plateau to the north of the Himalayas right here. We have the Himalayan mountain chain itself. And then we have the flat lowlands of India. So we have to explain all of these different features. Why is this area being pushed up? And why does the resulting mountain range have this very distinctive set of conditions? Why is it, earthquake rich but volcano poor? That differs quite significantly from other mountain ranges we thought about, like the Andes, which is very earthquake rich, but it's also volcano rich as well. Okay, so what about Japan? Well, in this case, we have a situation where we have two pieces of oceanic crust meeting. So we have a piece of oceanic crust up here and a piece of oceanic crust down here. straight away you'll notice that these pieces of oceanic crust appear to be at different heights. This piece appears to be slightly higher than this piece down here, so as a geologist we're going to have to explain that. Once again, we have one of these trenches running down here, so that's these linear depressions along the seafloor there. We can see it quite clearly. So we have another trench. We have to explain why that's there. But we also have chains of volcanically active islands as well. And these chains of volcanically active islands have a very distinct curve shape to them. And so we often refer to these curved chains of islands as island arcs. And so we can see we have one circular chain of islands here. So these are the Aleutian Islands that extend from Alaska all the way across the North Pacific, all the way over here to Japan and Russia. We also have Japan itself is another island arc right there. You can quite clearly see the curved shape. And then we have another island arc down here to the southwest of Japan. You can see the curve of the islands right there. Once again, we have another trench coming through right there. We can also see this area of raised terrain over here, and once again we have in fact two rows of volcanic islands. So there's our trench, and we can see we have one row of volcanic islands coming down like so, and then to the west of it we have another row of volcanic islands coming down like so. Once again we can see they have a gently curved shape to them. So we need to work out several questions. Why are these two pieces of oceanic crust at different heights? Why is there a trench here? Why do we have these curved chains of islands? Why are they volcanically active? There's lots and lots of things that a geologist has to explain. So if we look, here's our curved ridge, which consists of these volcanically active islands, our island arc environment. We obviously have another oceanic trench. So from a geologic point of view, this is clearly a very, very complicated area, and as geologists we have to try and explain why this is. So if we look at our next area, we're moving on to the Arabian Peninsula, and you can see that this is geologically speaking, a very, very complex environment. So what can we see? Well, straight away we can see we have obviously areas of continental crust and areas of oceanic crust, so got that down straight away. But we can also see we have several areas of elevated terrain. So we have this chain of mountains that's starting over here in Turkey. It's continuing through Turkey, through northern Syria, northern Iraq, into Iran, and then it's continuing over to Afghanistan and Pakistan, and then eventually over into the Himalayan mountains themselves. So we have this very large, very broad mountain range. Now, just like the Himalayas that we were discussing a couple of slides ago, we can see that in front of this mountain range here, there's no trench in the seafloor. So we have to explain why is there no trench here. But at the same time, we also have to explain why this area of elevated terrain over here, along the western side of Turkey, does appear to be associated with a trench-like feature. So we have a mountain range that on this end appears to be related to some kind of trench feature on the seafloor, but we have a mountain range over here that appears to be not related to some kind of trench-like feature. So we have to explain why this is. We also have to explain why we have this area of elevated terrain right here, the Afar region of Africa. Now, if you'll notice, this is in contrast to the relatively flat terrain of the Arabian Peninsula and the relatively flat terrain of northeastern Africa. So why does this area have this, this area of elevated terrain? Also, why is it very volcanically active? So we need to explain this. We also need to explain several features that we can see on the seafloor. Once again, you can see quite clearly we have one of these ridges running up here, and we can see it continues all the way to about here, where it happens to correspond with this area of raised terrain. But you'll also notice that there is what appears to be a very, very large crack running along the seafloor right here in the middle of the Red Sea. So we have to be able to explain this as well. So there's lots and lots of processes that appear to be taking place in this area. So obviously we have the Arabian Peninsula, which we discussed is an area of relatively flat continental crust. We have the Red Sea over here, which has this giant crack running down the middle of it. We have the Gulf of Aden here, which has one of these stepped ridges running down the middle of it. We have another oceanic ridge down here in the Indian Ocean, which appears to be connected to this ridge running down the Gulf of Aden. We have the Athar region, this area of raised continental crust over here, which is volcanically active. And then we have the Persian Gulf, which is an area of relatively shallow water here. And then obviously we have this mountainous terrain to the north of it. So there's lots and lots of things that we have to explain. So to sum up, we can see that the Earth's surface is a very, very variable area. And we can see that all the areas have lots and lots of different traits to them, and as geologists we have to be able to come up with a process to explain what we are seeing, and the process we're going to use to explain what we've just been looking at is plate tectonics. And so that's a very, very important point, and that shows you just how important the theory of plate tectonics is to geology, because it helps to explain what we actually see. It's what's called a unifying theory. It allows you to bring lots and lots of observations together and explain them using one grand model, essentially. So some of the features that we discussed are we have these oceanic fracture zones, these big faults that we can see running along the seafloor. We also have areas where we have isolated linear island chains. Now, we haven't seen a picture of these yet. We are going to discuss them in one of the other presentations, but let's just quickly touch on them now. So if we look over here, here we have the Aleutian Islands, and we can see the Aleutian Islands are stretching from Alaska over here to the Russia-Japan area over here. And we can see we have this trench that runs along the seafloor here. And we can see that it's produced a chain of volcanically active islands, which is approximately curved. It is an island arc. In contrast, you can see we have a chain of islands right here in the middle of the Pacific. So these are the Hawaiian Islands. In this case, you'll notice straight away, these islands, which are volcanically active, are not associated with a trench. You will also notice that instead of a curved morphology, which we can see here, the chains actually form a straight line. We can see one straight line here, then it changes direction, and then one straight line there. So unlike the island arc of the Aleutian Islands, which has a curved shape to it, we can see that these islands are forming a linear chain. So we need to explain to ourselves why in some cases we have volcanically active islands which are forming curved shapes and are associated with these trenches in the seafloor, but we also have some chains of volcanic islands which are not associated with trenches, and instead of having a curved shape to them, they actually form straight lines. We also need to explain our deep ocean trenches. We need to explain these mid-ocean ridges and why they have this very distinctive zigzag shape to them. We need to explain features like oceanic plateaus. So these are areas of raised oceanic crust which are relatively flat, just like the Tibetan plateau, but on the seafloor. So we need to explain where are these coming from as well, because you'll notice, as we can see, we have an oceanic plateau down here, which is well away from any major geologic feature. So you can see we have a ridge running along here. But we'll notice this oceanic plateau is well away from anything that we would consider to be geologically active, so we have to explain what's going on there. We obviously need to be able to explain the continents and why some areas of the continents are relatively flat and why some areas of the continents are relatively mountainous. We need to explain submerged ridges, and we need to explain island arcs, so for instance Japan. And we also need to be able to work out why we have the continental shelf. Why do we have these areas of continental crust which are overlain by relatively shallow seawater between 0 and 200 meters? So there's lots and lots of things that geologists have to explain, and we use the plate tectonic theory, the plate tectonic model, to help us explain what we can see on the surface of the Earth, including plateaus like Tibet. Okay, that's it everybody. Thank you for watching.